network, where we've mentioned convolutional kernel. And the last thing we were talking about was the decomposition of convolutional kernel. As you've seen in many, the size of the kernel will be very important because of the amount of computation involved. Guys, I just hope that you guys can hear me. Can you guys hear me? Right. So, so we have decomposition of a kernel. This is just an important concept in image processing and deep learning. This is often used just optimize convolutional operation just to reduce all the computation complexity that can happen when you are training a model. So this will involve breaking down a complex kernel into simple components, right? So we basically look at a kernel which can have a certain size. Maybe you have a 5x5, 3x3, depending on where how you want to use it. But the bigger the kernel, the more computation will be involved, which will affect your GPU as well because of the calculations involved in machine learning. So what is a convolutional kernel? So a convolutional kernel is just or again we also call it a filter. This is just a small matrix used to modify or extract the features from an image. So we take an image, we apply this kernel, which will try and take the pixel values and try to reduce it to certain values. So this is used like to make sure we have like edge detection in images, sharpening, blurring, and all those things. So this is used. So typically, we have kernels such as 3x3 or 5x5 or kernels that are larger than that. Okay, so a kernel decomposition means that we are factorizing a 2D convolutional kernel into a smaller or a different kernel. So we like multiplying the numbers of kernels. So this will reduce the numbers of computation while achieving the same effects that you can achieve. So this is especially useful when we're dealing with deep learning, where we have large kernels that are used in CNNs, like convolutional neural networks. So the type of composition that we can have like a separable composition. That means that we now create a 1D kernel. Example, if we had like a 3x3 kernel, which we have originally, and then we can decompose it into a simple kernel, such as having just a vector instead of having a matrix. All right, so that's one of the advantages of kernel decomposition, but this was more inspired by the ResNet network. Okay, so when we talk about decomposition, we have the ResNet network. So the ResNet or residual network. So this is just a type of deep convolutional neural network or deep CNN. This is just an architecture of CNN, right? The ResNet. So the ResNet is just a type of architecture which is designed to train deep learning network efficiently. So this is a method that was introduced, I think, in 2025, and this make your this provide the best image recognition when it comes to deep learning. So the main motivation for ResNet is that when we have deep neural network, okay, we as our network depth increase, that means the numbers of layer increase, we're going to achieve a better performance. That's the idea behind neural networks, right? We're going to achieve better performance. But the more network or the more layers we increase, the more we may also create other problems, such as your vanishing gradient problem. So we have vanishing or exploding gradient problem that can come during the training. So which means that now it becomes difficult now. So because we have these issues, the ResNet comes in and solve this problem using what we call residual learning. So residual learning is a method used by ResNet to solve the issue of vanishing gradient while we are increasing the numbers of layers in the neural network. So this method will allow gradients to flow more easily through the network. So the core idea, which is the residual learning. So the residual learning. So instead of learning a direct mapping for the data, so the ResNet will just learn a certain function, which we'll call a residual function. So and then create the network output. So it's going to skip certain steps to try and create that. So we have a residual structure which is used. So it's basically instead of learning the function that it needs to learn and go through that, it's going to skip and use a residual structure there. So this will be the residual structure that will be used. So we have different model of ResNet. You have, for example, your ResNet 18, which means if you see ResNet 18, it means you have 18 layers. Okay, so if you see ResNet 50, it means you have 50 layers ResNet. So if you see it in any book, when you have ResNet something, so that number shows the amount of layers. So advantages of using the ResNet is that it solves the vanishing gradient problem. So it's going to allow a very deep network and then improve the accuracy on image classification, detection, and segmentation tasks. There's also a faster convergence during the training. So this can be used as the backbone in many AI applications. You know, you have faster RCNN and different applications. So this is in image classification. You have, for example, ImageNet, your medical image analysis, object detection, face recognition. So you have it on this system. So not ResNet is residual network for deep learning. So it's a type of neural network that use a certain structure, which is called the residual learning. We'll skip certain connection to try and solve the issue of vanishing gradient. So this will allow training very deep network, right? So network that can go from 50 layers to 150 layers, and that can be trained without having a gradient, a vanishing gradient problem. Okay, so the residual structure that we have here is just the concept behind the ResNet, right? Which will allow the neural network to learn what we call residual mappings instead of directly learning the desired output. So which will make the training very deep, the training of deep network very effective. Okay, so this residual structure, it just it does mean that instead of this, you see this is the output f of x, which is an output like a series of layers, a residual function that we have, but the network will learn a different function with fx, function of x plus x. So the x here is just the input to the residual block. Okay, so the x will represent the input data, and then fx will just be the output convolutional layers in the block. And then so basically this function, we can call it y. So y will be the final output of the block. So this addition operation here, so we basically take the input plus the output. So this addition operation is called the skip connection or shortcut connections. So actually, that's what that means. Okay. So what problem are we solving? We're solving a vanishing gradient problem. That means it's a problem that always makes it difficult to train the model. Now, in this case, the gradient will just flow directly through the skip connection, and this will help us have neural networks with many layers without an issue of vanishing gradient. Right. So, and then we have different forms of residual blocks. You have your convolutional block and your identity block. So all work together. All right. So this is the architecture of the ResNet. Okay, so and then we're going to have the SENet. So the SENet is SENet that stands for squeeze and excitation networks. So this is another type of network or another architecture that was created in 2017. So the CNET is kind of an it's kind of an architecture that will enhance the representation power of convolutional neural network by just so. All right, so basically the CNET, the squeeze and excitation network, is a neural network architecture that will enhance the representation power of convolutional networks. So it was created in 2017, and it's really used for things like the classification task. All right, so the main motivation behind CNET is that when we have the normal or standard CNN, convolutional network, in the standard convolutional network, the CNN will treat all features channel equally. Remember, we have, let's say we have any feature that is being used to detect. So if we're looking at a picture, for example, if we're looking at a picture of a cat, so if image can identify the nose of the cat or identify maybe the ears of the cat. Okay, no, let me not take a cat. Let me take a rabbit, right? When you, as a person, as a human being, when you're looking at an animal such as the rabbit, the nose of the rabbit does not play the same role as the ears of the rabbit, because the ears of the rabbit show you immediately that I am dealing with a rabbit, because the ears play a bigger role in detecting that this animal is a rabbit than the nose. Because when you look at the nose of a rabbit, you can easily confuse it with the nose. So basically, the machine can identify, it's supposed to identify the nose of a rabbit as if it was the nose of a cat. But the ears are completely different. So with that idea in mind, so when we look at the standard CNN that we have, they treat all features channel equally. But when we think of it in reality, is that some channel may be more informative for a specific task. So for a specific task, certain features may be more important than other features. But unfortunately, the standard CNN will treat all features channel equally. So now, with this architecture of the CNET, so the CNET will have a mechanism to reweight these channels, which means that it's going to allow the network to focus on the most important features. So when we're looking at different features, so these features will have a certain way of being, like the value coming from different features in your network will not be taken the same way. So certain features are going to be more important than the other features. So in the CNET in the CNET structure architecture, the CNET will add mechanism to reweight the channel, which will allow the network to focus on the most important features. So the core idea is the reason why we call it CNET. So the core idea is the squeeze and excitation. So CNET will introduce a squeeze and excitation block that will perform the channel will perform the channel based on their importance. So we're going to have a few steps in that. So the first step that we're going to have a global informative embedding or global pooling. So the global pooling, we perform global pooling across the whole spatial dimensions of the feature map. So we're looking at all the features that we have, then we're gonna perform a global pooling, which will introduce certain formulas, where the system will introduce certain formula in order to see the importance of certain features. And then after the global pooling, we're going to have an adaptive reweighting of the features. Okay, so we're going to weight all the features and see what feature is more important than other features. So as I said, you can have it, and to understand it better, you can have an analogy with human attention. For example, human focus on important visual cues. For example, the eyes on the face, the wheels on a car. That's an example. So whenever you see an object, it has wheels, you're already thinking that immediate. That feature is very face, and then you see these eyes, then you can see, okay, that is a face because you've seen the eyes. So those are the features. So CNET will mimic this by letting the network informative channels. So an advantage of using CNET is just that it's going to improve the without adding too much or too many parameters. So when we're looking at any task that we're dealing with when it comes to image classification or the type of machine learning, when we're looking at that, we have so many parameters that we can try and make the system accurate in our classification task. Right? So we can have all those parameters that we will need to introduce, but the CNET will improve the accuracy without adding too many parameters. Okay, and you can introduce this architecture. This architecture can be integrated in an existing CNN architecture, such as the ResNet. So the ResNet can be combined with the CNET. Yeah. All right. So this will, as we said, note that the CNET is an architecture network that will of the CNN that will focus on the useful features, right? So this can be used in application scenarios such as image classification, object detections, or anything that you can have. Okay, so just to summarize that, the CNET, so the CNET is basically your CNN with squeeze and excitation block. The core idea is the channel-wise attention. That means we can reweight feature map. The two main steps will be the squeeze and excitation. The squeeze meaning we're going to have a global pooling to capture channel context, and then the excitation means that we have features channel network that will generate adaptive weight in order for us to see what feature channel is more important. So this can boost the performance in classification or detection tasks. All right. So okay, so we have main algorithm for object detection. So object detection, obviously, we're going to identify certain features, and then based on those features that we identify from an object, and we can be able to detect what type of object is that. So basically, there is many algorithms that can come and play. So traditional object detection and algorithm, we have like Cascade, HOGDPM, R, SVM, SVM, support vector machine, or other algorithm that can also come. So that is a certain algorithm that can play there. But obviously, most of these algorithms are not as accurate as using a neural network. Okay, so when we're using deep learning algorithm, in terms of neural networks, and the most used, the neural network that is used for image detection or object detection is the CNN, convolutional neural network. And we've noted that the CNN has modified version of CNN, such as the ResNet, the CNet. So those type of modified CNN that solve those issues that you may have if you just do a normal CNN without using this type of architecture. You're going to have a vanishing gradient problem. But if you're using the ResNet, you are avoiding that issue. So the two stages of object detection. Okay, so in traditional object detection, you're going to have to manually design the feature extraction factors. So basically, it means that those algorithms you're going to see, for example, if you have an image of a cat, you're going to specify that the features that you're going to use is the eyes of the cat, the nose, the ears, those part of the pictures or those part of the cat are going to determine how you're going to detect this object and classify that this is a cat or this is a rabbit. But when you're dealing with the emergence of machine learning, so in machine learning or deep learning, we don't need to specify those features anymore. But in deep learning, the computer itself will automatically extract the features. So there's no need to tell the computer to look at pictures and use the nose, the eyes, and any other part of the image as a feature. But the machine is going to take the whole picture and extract features or create features by itself. So basically, instead of you looking at a picture of a cat and looking at the nose, the ears, and the eyes and identify it as a cat, but in this case, the machine is going to look at the full picture and take each pixel and see the pixel value and create a pattern to identify the cat or the rabbit. So that's why deep learning is more advanced, because deep learning will extract the features by itself and actually create the whole feature map in order to be able to detect the object in the in the um, in the data. All right. So and then CNN, as we said, CNN, convolutional neural network, is used for image recognition. And then we have generative adversarial network, or GAN. So the GAN is a neural network which is used image generation. Remember, for image recognition, we use CNN. So image recognition means that we have data as images, and then the machine is going to be able to detect what image, what's the nature of that image, or what class of that image. So we have images of fruit. The machine will tell us what type of fruit is that, so that image recognition. But when we have image generation, that means we don't have an image, but the machine creates the image. Like what you see today, you have fake images of people, you have videos that are created today, You have people will look at an image and say, no, this is AI, and that's because it's generated. So the generative adversarial network is a neural network that will create those images. So that is used for image generation. So for image generation, we use the GAN network. So the GAN network, generative adversarial network. So this is one of the network that was also created in 2014. So the generative adversarial network, or GAN, is one of the popular model for machine learning. It has two parts. So it's going to have a generator and a discriminator. All right. So the generator is going to generate fake images or fake data. And the discriminator is going to discriminate or going to detect if that image is real or not. So this is how it's going, that this is what will happen. So we have that the whole processing of learning in a GAN is just, it's going to look at your data. So let's say you have pictures of cats. So take an image of a cat, it generates a fake image of the cat. So that fake image that was generated also becomes now Sorry guys, unfortunately, I just had that problem with the power, so my Wi-Fi went off and electricity, everything went off, so that's why it kicked me out of the meeting. Can you guys, can you guys hear me?
Yes, sir.
All right, so